In this section, we're going to look at another way of determining the indeterminate coefficients of a particular solution, this time using what's called an annihilator approach. Okay, so we begin with a definition, as always, or as usual. Let L represent an nth order linear operator specifically the one that looks like L of y. So it's an operator on a function y here. L of y equals a sub n d n y, where a sub n is a coefficient. dn is the differential operator to the power n. Basically, you're taking d1 would be the first derivative, d2 would be the second derivative, d3 the third derivative, and so forth. Plus another coefficient times another differential operator times y plus dot dot dot. I say times y, really it should be of y, because you don't multiply the differential operator times y, you apply it to y. But old habits die hard. These look like polynomials, and it really does look like you should say times. So that is actually, that's me misspeaking. It shouldn't be times, it should be d n minus 1 of y. But you'll hear me say times, and it's just because old habits die hard. These look like polynomials. Plus a sub 1 dy plus a sub 0 y, where this doesn't have any derivative applied. Here, we're going to keep these coefficients constant, where our coefficients a0, a1, all the way up to an are constant. Okay. If the characteristic polynomial of L, namely the polynomial a sub 0 times, and this one is times, m to the power n plus a sub, oh, that should be a sub n, shouldn't it? I want this to match the power. A sub n minus 1 m to the n minus 1 plus dot 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 plus a sub 1 m to the first plus a sub 0. If this characteristic polynomial is itself factorable, this is factorable, then we say that the operator L is factorable. Okay? So the operator is factorable if its characteristic equation is factorable, or its characteristic polynomial. Then we say L is factorable. Not only is it factorable, but we have some notation into what it factors into. Is factorable into L equals d minus r sub 0, where r sub 0 is simply going to be one of the roots of this equation, one of the things that makes this equation 0, times, right, so times PD, P for polynomial, where R0 is a root of the characteristic equation of the characteristic polynomial, and PD is just some other linear operator of degree that's one less than what you started with. And PD is an n minus first order differential operator. Okay. So this may sound pretty complicated, and I guess conceptually it's not the simplest thing in the world, but procedurally it's really pretty simple. Here, let's take a look at an example. If we have y double prime plus 5y prime plus 6y equals to 0, okay, then here you can write this using the character. You can write this in differential form. We can write this as d squared plus 5d plus 6 of y. Remember, this means take the second derivative of y, which is what you have here, plus 5 times the first derivative of y, plus 6 times y, like that, equals 0. So this is just the differential form of this ODE. But now, since this right here, you can think of the characteristic equation as just being this second order polynomial, here we can say, well, you know what? This factors. And in fact, this factors into d plus 3 and d plus 2, where the 3 and the 2 are roots of this characteristic polynomial here. They're the numbers that make this 0. So that's what we mean by it being factorable. Basically, if you take an ODE and write it in differential form, that differential, think of it as a polynomial, right? Because what you're doing is you're considering its characteristic polynomial. If that characteristic polynomial is factorable, then we say that the operator is factorable in the same way. Okay. All right, so now that we have the idea of what it means to factor an operator, now let's go ahead and define the main object of interest here to us, and that is, let's look at what an annihilator is. So let L be a linear differential operator, same as what we've been seeing up here, be a linear differential operator with, again, constant coefficients. And let's have f be a sufficiently differentiable function. Sufficiently differentiable? Yeah. When they say sufficiently differentiable, they just mean, oh, if it's a second order problem, we should be able to find at least the second derivative and have it be defined. If it's a third order problem, at least the third derivative. It doesn't matter how many times it's differentiable, as long as it's sufficient, as long as it's enough for this problem. Sufficiently differentiable function. Then let's see here. So okay, if L of f of x is equal to 0, you apply that operator to f and you get 0. Then we say L is an annihilator of f. L is an annihilator of f. Again, that sounds fairly complicated, but it is a simple enough concept in practice. Let's say I have the function f of x is equal to, let's say x squared plus 8x. Okay? If I applied the first derivative to this, if I said d of f, well, then that would get 2x plus 8. Yeah, that's not annihilated. It's not equal to 0. Okay, let me take the second derivative. If I said d squared of f, well, that would be the second derivative. That would give me 2. Still not 0. Okay, let me take the third derivative. Oh, that's 0. So d cubed is an annihilator of this function. Now, lest you think that that's the only one, look what happens if I take a fourth derivative. What's the derivative of 0? Well, it's 0 again. So this one's also an annihilator. If I take the fifth derivative, well, yeah, same thing there. So an annihilator is not unique, right? There's several derivatives that I could take, and all of those would give me 0 here. So this is the first of the annihilators, but there's others. So all of these here tell us that D3, D4, D5, and so forth are annihilators of this function f of f. Now you might wonder, okay, so what, I just take derivatives until I get 0? Well, unfortunately, that doesn't always work, because think about an exponential function. If I have e to the x, it doesn't matter how many derivatives I take, I never get 0. So you say, okay, so some functions just can't be annihilated. Well, I didn't say that. I just said taking a straight derivative doesn't work. Depending on what kind of function you have, you may have to get a little bit fancy with these operations. However, in this course, you've seen so far that most of our answers revolve around being polynomials, exponentials, or trigonometric, sine and cosine. Right? We haven't really seen much else. So for now, we're going to stick to 3 types of annihilators, 3 groups of annihilators. And they're exactly those, the ones that get rid of those 3 types of functions. So here I will write this as a note. The 3 kinds of annihilators we're going to care about. If you have dn, so just like what we have over here, right? d2, d3, d4, like that, these are going to annihilate polynomials. And they annihilate any polynomial of a term that is less than this one. Notice right here, if I had a second order polynomial, d2 was not enough to annihilate it. I needed d3 to annihilate it. So I need one more here, one higher order than the degree of my polynomial that I'm trying to annihilate. So this annihilates not x to the n, right? You would need more than n to annihilate that, but it annihilates x to the n minus 1, x to the n minus 2, x to the n minus 3, and so forth and so on. Anything with a lower power. Exponentials are annihilated by something that looks like d minus a to the n. And that, oops, I don't know how to spell. Let's try that again. This annihilates x to the n minus 1 e to the ax. It annihilates x to the n minus 2 e to the ax, all the way down to x squared e to the ax, x e to the ax, and even just e to the ax by itself. So it annihilates e to the ax or e to the ax times any polynomial, any monomial term here with a power that's less than this n. And finally, the last one that we may concern ourselves with here is going to be d squared minus 2ad plus a squared plus b squared. Oops, let me keep these all lowercase. B squared, like that, and all of that raised to the power n. And this is going to annihilate anything that looks like x to the n minus 1 e to the ax times sine of bx. So here the a is the coefficient, a is the coefficient in the power of the exponential, b is the coefficient inside the argument of the sine, and it annihilates x to the n minus 2 e to the ax sine of bx, but this sine can also be replaced by a cosine. So it'll also annihilate things like x to the n minus 1 e to the ax cosine of bx, x to the n minus 2 e to the ax cosine of bx, like that. This is by no means an exhaustive list of annihilators. There are many, many more, but these are really the only kinds of functions that we've seen so far anyway, so that's what we're going to concern ourselves with here. Those are the ones we really need. So for example here, if I had something like f of x equals, I don't know, let's do x to the power 5 plus 8x to the power 4 minus 6x to the power 2 plus 12. All of these are monomial terms that are stitched together to form a polynomial. All of these have a degree 5 or lower, which means they're all annihilated by d6. Are annihilated by d6. Or higher, if you had d7, d8, d to the 9, any of those would work. Okay, but this is the smallest one that I can find here. Let's see, if I had a function g of x, which is equal to, let's say, 8e to the 2x minus 5x squared e to the 2x. Here, this is a monomial term times an exponential. So all of these, well, notice that the biggest power among any of these is squared. In fact, this doesn't even have x to a power. So you have exponentials times x to the, at the most, squared. Okay. So then over here, I'm going to have d minus a. Right? Here, where a is the power in my exponential, so here that's going to be a 2. These are annihilated by d minus, and again, a is my 2 here, the coefficient in my exponential, d minus 2 to the power of n, where again n is 1 higher than the biggest power you see here. Since the biggest power you see here is 2, then your n is going to be 1 higher than that, so that'll be 3. That'll be annihilated by d minus 2 to the power 3. You can actually try that Like you can actually take the derivative of this minus double this 3 times, and that'll give you 0. You can actually try that annihilation, and it'll give you 0. Then h of x, that's going to equal to, let's say, 5e to the 4x sine of x plus, let's say, 9e to the 4x cosine of x. Okay? These are both annihilated by, annihilated. Annihilated is one of those words that even when I spell it right, it looks like I spelled it wrong. Annihilated by, well, let's see. I've got d squared minus 2. Now, a is going to be whatever the coefficient is here in your exponent. So since that's a 4, that's going to be 2 times 4. So it'll give me 8d plus, and then again, your a is that 4. Your b is the coefficient inside of the trigonometric functions. Since this is 1x, well, then b is 1. So I have 4 squared is 16, and then 1 squared, that's just 1. 16 plus 1 will be 17. And then the power, this n right here, is just going to be 1 higher than any of the powers of x that you see here. You say there are no powers of x here. Okay, well, that's x to the 0 then. So 1 higher than that would be x to the first. As usual, if you want to put first power, you can. If not, leave it off. So these would annihilate, this would annihilate these, this would annihilate these, and this would annihilate these. And again, these are not unique annihilators. There are others that would work, but for our purposes, as long as you can find an annihilator, that's plenty. You just need one. Okay, so now why on earth would we want to do this? Well, think about it. What we're looking for is the solution to a particular, we're looking for the particular solution to a non-homogeneous problem. But what's making that hard is the fact that you have a non-homogeneous problem. If your problem was homogeneous, things would be easy. All right, then we could just use the characteristic equation and we'd be done very quickly. But what do annihilators do? Annihilators take functions and, well, they annihilate them. They make them 0. Oh, so you can take a non-homogeneous function whose input function might be something like this polynomial, this exponential, this combination of exponentials and trigonometric functions, and it annihilates them and makes them 0. In other words, annihilators, for our purposes, are going to be used to turn non-homogeneous problems into homogeneous problems. So let's give this a try here. All right, so we're going to solve, let's do y double prime minus 2y prime plus y equals x to the third plus 4x. Like that. Non-homogeneous problem. Again, if this was 0, this would be an easy problem. I would just take this factor, find the solutions, done, right? But the fact that this is not 0 makes this non-homogeneous and makes this a much longer problem. Okay, well, let's take a look. First of all, this right here can be written in the differential form. Second derivative, I can write that as d squared minus 2 times the first derivative, that's 2d, plus just a single copy of y, that's just plus 1 of y, equals x to the third plus 4x. Okay, here nothing's really changed. I've just written it in a different form, the differential form. Okay? But now I look at this and I go, oh, look, I've got a polynomial. I've got terms whose degree is 3 or less. Here, this will both be annihilated by d to the power 4. These are both of the terms are annihilated by d to the power 4. So what I'm going to do is I'm going to do that. I'm going to apply d to the power 4 to both sides. I've done a pretty good job of not saying multiply. I say apply. Remember, these aren't actually being multiplied. It just looks that way. But that look is on purpose. It's meant to make things look more algebraic than they really are. All right, so now, because this is an annihilator of this function, this side is now 0. Oh, but now it's a homogeneous problem. This is much easier now. I can now consider a characteristic equation here, an auxiliary equation. I can now write this as m to the power 4 m squared minus 2m plus 1 equals 0. This is now my auxiliary equation, my characteristic equation. And I can solve this. Hey, look, this one's m to the 4th. I can't really factor that. This one I can factor a little bit. This one's going to be what? M minus 1 times m minus 1, which I'll just write as m minus 1 squared. Because the auxiliary equation is now factored, I can solve. Here, look. This is, well, m's got to equal to 0. Now here, this happens 4 times. So it's m1 equals m2 equals m3 equals m4. So it's 4 instances of it, but it's still just 0. Here, m would have to equal to 1. Okay, well, that happens twice. Okay, so m5 and m6. Not plus, equals. M5 equals M6 equals 1. And there we go. What do you mean there we go? Well, there we go. We have our roots of our characteristic equation. That means we can now write down our solution. We have that y is equal to, well, let's see. I've got, I'm going to start with these. Can I start with these? You can, but I'm going to start with these for a reason that you'll see here in just a moment. I've got m5 equals m6 equals 1. Okay, so I've got c1 times e to the 1x plus c2. Now, I have a repeated root, so that's going to be the same as before. It's still going to be e to the x, but I'm going to multiply it times x. That's what we do with repeated roots of a characteristic equation. And then over here, I've got 4 roots repeated. Okay, so that's going to be what? c3 e to the 0x. And then all the rest are going to be the same as this one, but each time I'm going to multiply by another x. So I get c4 x e to the 0, and then I get c5 x squared e to the 0, and then the 4th time I get c6 x to the 3rd e to the 0. Okay. E to the 0 is equal to 1, so all of these are just 1. 1, 1, 1 all the way down. And so I get my solution, y equals c1 e to the x plus c2 x e to the x plus c3 plus c4x plus c5x squared plus c6x to the 3rd. And there's our solution. But the more observant of you may notice a problem. You say, what, you made a mistake? No mistakes. At least I hope not. I don't see any mistakes. But no, the problem isn't that there's a mistake here. The problem is we're not done yet. You say, what are you talking about? There's your solution. What else could you want? Well, this is a second order problem, isn't it? Yeah, second order. So then how come its solution has 6 undetermined coefficients? How come its solution has 6 parts here? Shouldn't a second order problem only have 2 parts? You say, yeah, but that's only if it's second order with 0 here, if it's a homogeneous problem. This was a non-homogeneous problem, so obviously there's some other terms besides just these 2. Well, yeah, but those other terms shouldn't have indeterminate coefficients. Basically, what we have here is 2 of the terms from this are going to be my complementary solution. The rest are going to be my particular solution. So we look at this and say, okay, well, which is which? Well, notice right here, the starting problem was not this whole thing here. It was just this one, d squared minus 2d plus 1. So this one here gave this part of the auxiliary equation, and this part of the auxiliary equation had those 2 roots. So those 2 roots are in these 2 terms in my solution. So this accounts for my complementary solution. This is my y sub c. I leave those alone. That's exactly the way it's supposed to look. But if those 2 are my complementary solution for a second order problem, all the rest of these must come from the particular solution, from the fact that this is a non-homogeneous problem. And particular solutions, or y sub p, are not supposed to have undetermined coefficients. We now need to figure out what these guys are. You say, well, okay, so this is kind of like what we did in the last section, right? Yeah, very much so. Okay, so then why do we need another technique? Couldn't we just do it the way we did in the last section? Yeah, actually, you probably could. These 2 sections are both about determining the indeterminate coefficients of our particular solution. And in a lot of ways, they're interchangeable. If you can do one, the other one would give you the same result. However, there is just enough difference that you might have a preference. You say, well, which one should I prefer? Oh, that's up to you. It's a preference, right? But what I will say here is that in our previous section, we didn't have to worry about annihilators, right? This requires a whole new concept that we don't need in the other section. On the other hand, in the other section, we had a possibility of when we chose a particular solution, there was a chance we chose wrong, and we had to go back and edit it after figuring out that we did it wrong, and so we lose a little bit of time there, a little bit of effort. Here, that's not going to happen. We know this is our particular solution. There's no chance this is the wrong one. So which is the better technique? It's kind of up to you. This technique requires you to know what an annihilator is, and it requires you to remember a few basic annihilators. We're not going to have more than these, but you would have to remember these. But the upside is you will never have a misleading particular solution. You'll never have, oh, that was the wrong guess. You have to try again. On the other hand, the technique from the last section is kind of the opposite, right? You don't have to learn any annihilators. You don't have to remember any of this. But the actual work may lead you down the wrong path, and you may have to make some edits and restart the problem on occasion. So whichever one you choose is up to you. They really are just a matter of preference. But the two sections they're giving you the same kind of answer. So really, it's a matter of your preference. So here, let's go ahead and finish this one off to find out what these coefficients are supposed to be. And the way we do it is, well, we just take our particular solution, plug it back in. Let's see what we get. Here we get that y sub p. I'm just going to write this down again. Instead of writing C3, C4, C5, and C6, I'm going to go back to A, B, C, and D. I'm going to write this as A plus bx plus cx squared plus dx cubed. And the only reason I do that is because it's slightly less to write, and there's a slightly lesser chance that I'm going to mix up a symbol somewhere. Okay, so let's see. This is a second order problem, so I need to find up to the second derivative. Y sub p prime, that goes away, and I get b plus 2cx plus 3dx squared. And then I've got yp double prime, that goes away, and I get 2c plus 6dx. So now I take this right here, and I plug it all in. Okay, so let's see, what have I got? I need y double prime. So that's going to be, what's that? That one on the bottom. That's going to be 2c. Let's see, what do I have? 2c plus 6dx. And then minus 2 times y prime. Okay, so minus 2 times. My y prime is this one here, my b plus 2cx plus 3dx squared. And then I have plus my y, which that's my y right there. So I've got plus a plus bx plus cx squared plus dx cubed. That is my y double prime minus 2y prime plus y double prime minus 2y prime plus y, and that's supposed to equal to my original input function here, my x cubed plus 4x. And now we just set up our system and solve for A, B, C, and D. All right, so here we go. Let's see. I'm going to group all my cubic terms. There's only one, so let me just put that one up front. So I've got dx cubed plus. Now squares, I've got one here and one here. So I've got cx squared and then minus 2 times 3dx squared. That'll be c minus 6dx squared. C minus 6dx squared. Gathering my linear terms, I've got a bx here, and I've got minus 2 times 2cx there, so that's minus 4cx. So I've got b minus 4cx plus b minus 4cx. Oh, and I've got another one over here. I've got a 6d here, don't I? Oh, let's not lose any terms. I've got plus, so I've got b minus 4c plus 6d x. And then finally, I've got my constants. I've got an a right there. I've got a minus 2b here. And I've got a plus 2c over here. Okay. And that's going to equal to x cubed plus 4x. Okay? So here already I know that d must be 1, because if dx cubed has to equal to 1x cubed, well, that means d is equal to 1. Okay, there we go. That's nice. This next one tells me that c minus 4d has to equal to 0, because over here there is no x squared in my input function. So if this x squared must equal to no x squared, well, then this must equal to 0. So I got c minus 6d equals to 0. Oh, we can plug that in, right? So c minus 6 equals 0, which means c must equal to 6. That way 6 minus 6 times 1 is equal to 0. The next one tells me that my b minus 4c plus 6dx must equal to 4x. So this must equal to 4. b minus 4c plus 6d equals to 4. But of course, you can always just plug these in here. Let's see. C is equal to 6. So I've got b minus 4 times 6 is 24. Plus 6 times 1 is 6 equals 4. And then I can go ahead and take what? Negative 24 plus 6 is negative 18. And add that to the other side. That gives me b is equal to 22. And finally, I can get this constant here must equal to 0, since there's no constant here. So a minus 2b plus 2c equals to 0. But of course, I can plug in my known values. A minus 2 times, well, let's see, b is 22, plus 2 times c was 6 equals 0. What have I got here? I've got negative 44 plus 12, that's negative 32. I can add that to the other side, and I get a is equal to positive 32. So now we're done, because now we have our indeterminate coefficients, and we can go ahead and plug those back in. So coming back to our previous problem, we take our A, B, C, and D and plug them in here, and we get our result. So that means that y is equal to, again, this is our complementary solution. We don't find any values for this. We leave it as it is. C1 e to the x plus C2x e to the x plus, and then here, my A, my B, my C, and my D, I just plug them all in. So I get 32 plus, let's see, 22x plus 6x squared. And then finally, my D was 1, so I just get plus 1x cubed. And that would be my general solution to my original non-homogeneous problem here. And that's it. That's it for this problem. That's it for this section. If you have any questions, comments, or problems, please let me know. And I hope you all have a nice day.